There you go.
Okay, everybody. Well, welcome to our September meeting of the Howard Astronomical League. Today is an auspicious day because we're back in person and I'm wearing the wrong glasses. Yeah, I can't see anybody. All I can see is up close. So we have a really nice, well, we got a nice meeting plan. We have a great speaker and we have all sorts of great pictures to share. And I'm super pleased to see quite a few people made it here. I didn't know what to expect. So I'm glad we got 2, 4, 6, 8. We got 12, 13, including me. Lucky 13. Okay. Anyways, let's go ahead and get started. If I can do this.
This is me, Dan. Can you all hear me?
Yes.
Hi, Dan.
Listen, I had something to say really quick. Did you all get the picture of the Big Dipper I emailed?
Yeah, we're going to show it during the meeting.
I would like to present that tonight.
You will be able to do that when the time comes.
Thanks, because I want to give it. Thank you.
There you go.
Okay, so here's our agenda for tonight. We'll go through some introductions, make a few announcements of current events. And I just remembered that there's at least one that I forgot to put on there, but we'll bring it up anyways. And then we have an excellent speaker from the Space Telescope Science Institute right here in Baltimore. And then we'll go through our regular what's out in the sky this month, and then share some images. And we got lots of nice images this month. So I'd like to start with introductions. Is anybody new online? Are there any new people online? Anybody want to introduce themselves and say hello? Any old members who haven't been here in a long time who want to say hello?
Victor, are you trying to call me out?
Yeah, maybe. It's really nice to see you here.
It's good to be here. It's good to be seen.
Yes.
Except you're not showing video.
Yeah, I am. There we go. How's that? So anyways,
Yeah, I haven't been on for a while either, but I'm back after several months of hiatus.
all right, well, I'm glad you're back and I'm glad you submitted a picture.
Oh, good.
Okay, well, if there's nobody new,
Yeah, maybe here in the room.
oh, anybody new here in the room? Thank you. Yes.
I'm pretty new. I'm Cindy Coquiaro.
Hi, Cindy. Welcome.
I'm a recent member as well, Anthony Bonds.
Okay, great.
Yeah.
You guys new to the hobby or new to the club or both?
New to the hobby. It just started like in the spring.
Okay, great. Well, I hope that this is a good place for you to learn a bunch of new things and meet like-minded people.
Right, and it's something we haven't been able to do for a long time.
Yeah.
Welcome.
Yeah, that's right. Welcome. Hello.
Yeah.
All right. All right, well, I'll just move on then. If I can. Boy, I'm really struggling with this.
That's right. Go down the bottom like you did before. This is what happens when there's a writer's strike.
Wow, that's crazy.
Yeah, I'll get it later.
Okay, so announcements. We have our public star party coming up this weekend, although I don't think the weather's particularly cooperative. Seems like it's going to cooperate very much. I also wanted to say a quick note about the impromptu star parties that don't forget to keep your eye out for them. We had a couple of good ones these last few days, and sorry. And we also had a remote impromptu star party out in dark skies, and we had a few people show up for that, and that was quite excellent. I got my first experience looking through an 18-inch Dob in Bortle 3 skies, and it was amazing what you could see. So keep an eye out for those. If you're not on the impromptu list and you want to be, that you can find a link right on the main Howard Astro page. There's another thing happening this Saturday, which didn't put on the. Phil, do you want to talk to
Sunday?
is it this Sunday?
Yeah, Robinson.
Yeah, there's an event right here at the Robinson Nature Center.
So the Robinson Nature Center every year has their an annual event here where we're usually out on the green roof, which is literally right above us here, a couple stories up. And but the weather is going to be probably not cooperative for solar. So what we're going to do is we're going to have a table set up for HAL, and we'll be able to talk to whoever's here at the event, about HAL, and we'll have some information about the sun and whatever else we want to show there. So we've had to do this in the past when the events got rained out, but it happens every September. We've been supporting it for almost as long, if not as long, as the Robinson Nature Center's been here.
So that'll be this Sunday, the
This Sunday, yeah,
24th.
from like noon to 6, I think it
Noon to
is.
6. Okay.
Noon to 5.
And
Hey, Victor, can I jump in just real quick?
please.
I just want to remind people that the impromptu star parties are for members. So
Okay.
if you're not a member, but you want to attend one of our impromptu star parties, please join.
Did you have an experience with a bunch of with some non-members?
Not a bunch, but there's been a few that showed up. I think some of them may now be members, and thank you very much.
Okay, well, great.
Right.
That's good to hear.
And it's a separate list for
Yeah.
members to opt into.
Yeah,
Right.
that's right. Just because you're a member of HAL doesn't mean you're a member of the impromptu list. So if you are a member of HAL and you don't get the emails, basically the impromptus are ad hoc or messages that come out when there's going to be a clear weather, when one of the members who's a key holder decides to just open up the park, either Alpha Ridge or Carr's Mill, or sometimes even a darker site out west, and invites you to come out and join. So you get last minute notification if you're on that list, which can be nice, because the weather is not always cooperating when we have our scheduled parties, as is happening this week. So let's move on. Next thing is book of the month. Crystal Rowland normally discusses this. This is my choice this month. I got to choose somebody, but I kind of piggybacked off of one of her earlier books of the month by choosing the same author, because I enjoyed reading this guy. The earlier book was Bad Astronomy, and this one is called Under Alien Skies, A Sightseer's Guide to the Universe. And I'm not all the way through the book yet, but I'll just say it's very beginner friendly. You don't have to know very much to enjoy this book. And he kind of describes the experience that you would have if you were, the things that we look at as deep space objects. He kind of describes us from using a scientific and physics-based explanation, what you would see and what you would experience if you were there. It's kind of fun. It's a very easy read.
He's a really nice person.
Okay.
Is he the same guy that was on how the universe works from NASA?
I don't know. I'm not.
Well, he actually taped all those, the how-to astronomies, like the crash course astronomies. He taped all of those.
Okay.
Cool.
Anyways, the book's fun. Without further ado, we can go off into our club stuff, but I think it would be really good to jump straight into our speaker, because we have a great speaker, Alyssa Pagan. Is it? How do you say your last name?
It's Pagan, but no worries. It's a very confusing spelled name.
Okay. So Alyssa's a science and visual developer who works in the Office of Public Outreach within the STSI. And with her background, she works closely with astronomers to help create the images that are put out for the public viewing, to educate and inspire and showcase our universe. So without any further ado, I'll let you share your screen.
All right.
Everybody see those?
Yes.
Go. Okay, great. Well,
Yes.
thank you for having me, everybody. I am Alyssa Pagan, and I'm just going to talk a little bit of how we process images, create color imagery that support news releases, so science discoveries from observatories like Webb and Hubble. But this process can be applied to all observatories, not just these, and even your own process if you have your own rig, which you guys probably have, and I'm probably jealous of that. Because I don't have one. But before I get too far into the process, I think it's important to reflect on how we got here in the first place. How are we getting these beautiful images that we get because we have amazing data and science, and sort of the things that we can expect to see based off of what we know about the telescope. And so I like to go back to launch day. So that was Christmas Day, 2021. I don't know if you guys remember where you were. I know I did. And I watched the launch on my couch in my pajamas at 7:20, and I got everybody up. And it was a very, very exciting time. So yeah, it was very, nerve-wracking, but we know that it was successful. And then you could think like, oh, the worst is over, right? But that's actually not the truth. The worst was yet to come. So we have to actually unfold this rocket in the air. We have to unfold the telescope because it had to fit in the Ariane 5 rocket. And as it's doing this, it has to travel a million miles away to this Lagrange point 2, which is going to orbit. So just a lot of things had to go right in order for this to work and actually see the images that we do. So you can think of, it was over 344 single points of failure, just meaning like if any of those single things went wrong, this telescope would not work. And that's crazy to think about. I'm glad I didn't know that number before. I only learned about it afterwards, but it's just crazy. So all those things that you have to think about, from its unfolding, a tennis-sized
That's good how it is.
court. And then we have the 18 hexagonal mirrors that have to align, and we have to calibrate them. We have to calibrate all the instruments. Again, unfolding the sun shield. And then it's again traveling to this 100 million miles away where it can't be serviced. And at the same time, we are cooling the instruments. But they have to cool very slowly, so there's no ice in order to actually see in infrared. So all these things went right, luckily. And not only was it fully successful, it was actually more successful than we predicted. And we actually extended its life. So it was like 5 to 10 years, and now it's estimated 20 years of life in space, which is great. And then this is just sort of like a sanity check of the alignment, which is from this pupil image. It's a pupil image. It's a pupil camera in the NIRCam instrument. It was very unexpected, but it was very cool to kind of see this. Just showing that everything is working. Of course, we get a calibration image that actually shows us the true, alignment. But it's cool to look at this because you actually see the signature of this instrument in the images that we see, which is like the diffraction spikes of these stars. So the hexagonal 6 points actually create the 6 spikes that you see, the 6 prominent spikes, and then the secondary mirror, the struts that are holding up the secondary mirror, create 3 other spikes, but some of them overlap. So that's why you get this sort of 8-pointed spike look to these Webb imageries. So it's just cool to note that. And then this is this alignment evaluation image, just to let us know everything's working great. And it, wasn't supposed to be this beautiful image, but it ends up being that way because Webb is so sensitive. You get all these background galaxies in here. So it's just kind of a nice bonus. And I will be focusing specifically on imaging today. So imaging modes. So specifically the near infrared camera, or the NIRCam, and then the MIRI instrument, the mid infrared camera. But I feel like I'd be remiss not to mention other instruments like NIRSpec, and the fine guidance sensor and NIRIS, all these things that support spectroscopy, which is very important to actual science. And about 75% of Webb's is based off of this spectra. It's very, very good stuff. But again, we're just going to focus on images today. So why do we care about infrared light? Why do we need an infrared telescope in the first place, like Webb? And so we're probably all familiar with the electromagnetic spectrum of light, and what we can see is just that small portion of visible light. But then on the right of this diagram, it extends to the shorter wavelengths, or the higher energy wavelengths. And then on the left side, we have the lower energy wavelengths, the longer wavelengths, which include infrared. And if we could only observe what we could actually see or understand what we actually see, we'd have a very limited understanding of the universe. And we also wouldn't be able to use a lot of the technology that we rely on now, just from simply like turning on the TV, placing a phone call, putting something in the microwave, just all of that stuff that we rely on to function day to day. And so a nice way to think about infrared is looking at the predator. predator vision. So you're kind of getting like a heat signature. That's why there's actually some predators in real life that can like see, through bushes and things like that. It's very helpful for that sort of technique. I will say that mud will not protect you. You will still be found. But a more realistic application of infrared light, or how we use it, is actually for face mapping for your phones, to unlock your phones, and then these little bits, these points of infrared light map your face, and then it actually doing this like every couple of minutes. And that's why you are able to unlock your phone, even if your face is changing over time, or if you have glasses on or you don't have glasses on. So. And then so how we extend this to space is we can think of this visible light image on the left, where we have a scientist using a trash bag. And you can think of that as like dust. That's opaque, can't see it in the optical light. But in the infrared light, where you're detecting the heat, you can see through the bag. So you see the heat. And that's exactly how we look at space in these different wavelengths. So on the left, we have a Hubble image where we see the galaxy as we normally would see it, where it sort of has this bulge in the center that's red and orange. We have these young stars on the spiral arms, and then we have that dust that's obscuring everything. Now on the right, we can not only see through that dust, but if we go a little bit further into the mid-infrared, this is what Miri on the right is, you're actually seeing the dust emitting. So you're going a step further from seeing through to actually seeing the dust emit itself. So this is why we want to have very different telescopes to do these different things. And then another concept for why we like infrared light, or why we need to detect infrared light, is a concept called cosmological redshift. So basically that just means over time, these very distant galaxies and stars are radiating light, and over time, as space is expanding, their light gets shifted and it gets redshifted into the infrared. So we can only detect it in the infrared. So very important for understanding sort of cosmology, age of the universe and things like that, just a step further than Hubble could give us. And then it's a space telescope because I'm sure, as you guys are probably more familiar with, the atmosphere can be very problematic for seeing. And of course, we can't actually detect infrared light from the ground because the atmosphere mostly absorbs infrared light. And as I kind of mentioned before, Webb is not a replacement to Hubble. It's intended to work in tandem because we want to understand these different wavelengths to get a full picture of the universe and understanding of it, just like we have different medical equipment to see in different wavelengths, like X-rays to see your bones. We have MRIs to see soft tissue, etc. We want to get the full picture. So why do we make color images in the first place? So I feel like I don't need to convince you guys of why we do this, but there's things that we like to keep in mind that sort of inform our decisions throughout the process of creating these images. And of course, the first thing is we want to visualize the data. So data is very important, to get scientific research done, to get scientific analysis, data analysis. But in terms of getting the bigger picture, we want to see it, actually see it. And then we also want to illustrate these scientific discoveries and concepts. We want to make this available to everybody. We wanted to make it accessible. So it's not just for scientists to understand, we want to get the general public engaged. And so that ties into the last part, which is we want, again, to make astronomy accessible. We want people to be excited about it, enthusiastic about it, and potentially inspire like a whole new generation of people, engineers, scientists, etc. Just anyone who's interested. Okay, so I talked a lot about that. But how do we even get the data in the first place if you wanted to process an image from Webb, from Hubble, etc.? So actually, this data is all public. So you can find all the data that's been taken from Webb, from Hubble, and other observatories at the MAST, or I should say Bara-Mikulski archive, which is hosted by Space Telescope Science Institute. And you can find it at the link below, mast.stsci.edu. And so all the raw data and the calibrated goes into this archive. And so you could actually take the raw data and calibrate it yourself if you wanted to, using this Python pipeline, or you can just use the default parameters that this archive already implements. So you already have calibrated data for you. So it just kind of depends on what you're interested in. If you want to skip sort of the more data reduction sort of technical side and then get to like the post-processing side. But you can find all of that here. Though it can get a little bit weird to navigate, can be a little convoluted, but there's some tips in order to get to the data that you want. One easy way to do it is if you see an image that you really like on webbspacetoLescope.org or any sort of NASA site, You can actually go on STSCI's webtelescope.org. There's a fast facts section underneath of the object that describes things like the name, so like the astronomy catalog name, the coordinates, and most importantly, or I should say the easiest thing to work with is actually this data description. This is a proposal ID, which will take you directly to the data. So you don't really have to do any searching. There will be a filter that you can select to put in this number. Now, of course, if there's just, you're just interested in a particular celestial object and the catalog name, you can work your way down and refine it. That's fine too. This is just kind of an easier way to get directly what you want. Okay, so this is the archive here, and I'm just using M16 or the Eagle Nebula as my test subject here. So I'm putting M16 in the object name, and then for the mission, I'm putting JWST. Now, this is a lot easier to query JWST stuff because, it's relatively new, so you're not going to get a ton of data all at once. So I've actually only have 13 queries here. But if I click search, then I can sort of refine it down even further if I do have more. I think 50,000 queries is like the limit, so you have to kind of refine it before you get to that point. But what's kind of nice is that you do have this like viewfinder here that shows you the footprint of whatever instrument you're looking at in the sky. So you can kind of see that there's the Eagle Nebula, or the Pillars of Creation, I should say, in this region right here, which is what we want. And then I'll be focusing on the near infrared instrument, or the NIRCam instrument, because that's the highest resolution data. And so it's just really fun to work with. Now, I should mention that these files are huge. So if your computer can't handle it, maybe you want to start with the MIRI data, which is like much smaller. So just something to think about. And so, yeah, I think each one is about 5 gigabytes, but that's because it contains more than just the 2D image. And we'll get to that in just a second. But anyways, if you want to process your image, the first thing you want to do is you want to select all the filters that were used for that instrument, for that object. So I have the 6 filters that were taken for the Eagle Nebula, or the Pillars of Creation. And you can see that category of filters. It has the filter names, and this is just saying the filter, and it's saying 1.87 microns. And if you get an N or a W, that's just referring to narrow band, wide band, and things like that. It's not like the best sort of names, but if you get a little bit confused about the filter names, there's always a data handbook that's available as well. But anyways, you want to select all of those, and it might seem like you actually have 2 of the 4.4 micron filter, but that's actually not true. It's masquerading as one of the narrowband filters, because the narrowband filter actually passes through, or I should say that it passes through the wideband filter first, because there's actually 2 filter wheels on Webb. So that's why it might look like that. So after you've selected that, then you'd want to click the download basket, or you'd take it a step even further. You can refine a little bit more. So I was talking about calibrated data and raw data. So I have minimum recommended product selected right now. And that's just if you want the calibrated data. And usually that is good, like that's good quality data. The default parameters of the pipeline work very, very well. And it's rarely you'll want to reprocess them yourselves. Sometimes the scientists for us will reprocess it through the pipeline if there's like very specific background subtractions or very specific things that need to be touched up. But for the most part, this is good enough. But again, you are able to get the raw data files and run it through the Python pipeline if you want to, if you're very interested in sort of the programming side of this. And so, oops, I went a little too fast here. Let me go back. So yes, here I'm just selecting the 2D FITS files. That's all I want, are the image files. There's some other FITS files here, but these are all that I want. And then I'll select download, and then I'll get a lot of data. And this is just the overview of this little calibration pipeline, or I should say large calibration pipeline, where all the Webb raw data goes through. So it's just the first stage, just all the data goes through this detector 1 step or stage. Then it gets separated between the imaging mode and the spectroscopy mode. And then again, for different types of modes, from spectra to coronagraphs and images and etc., until it's completely calibrated. And then both the raw and the calibrated go to the archive. And if you're really interested in this calibration pipeline, you can go to this link right here, and there's a bunch of like videos, there's documentation, anything. If you just kind of want to play with the steps, there's a lot there. But just in
Alyssa?
Yes.
This is Victor.
Yes.
Sorry, I was kind of working a couple of technical issues on my end for a second, and I may have missed it. But this is what you do, and this can also be done by the public?
So I don't do the pre-processing. That's not usually something that I have to do. That's usually something that's done automatically by the calibration pipeline, even before it hits mast. And sometimes the scientists will. So my job is mostly actually the post-processing that comes from this. So
Which is what you're walking through now.
yeah, so this is right
Are you
at
saying people, just members of the public can do this as well?
yes, yeah. So the
Wow.
raw data is available if you want to calibrate the data, and then of course you can just do the post-processing as well. Yeah.
Awesome.
Yeah. Yeah, and if it's not immediately available, because sometimes there is a little bit of an embargo between when the scientists get the data and when it's released, usually with their paper. So there might be like a 6 month to 1 year max embargo, but eventually all the data will become public.
I see that Chuck has his hand up. Chuck, do you want to ask Alyssa, do you mind if we ask questions as you go, or do you want us to hold them?
Oh, not at all. Yeah, feel free, whatever works.
Question, I think Wayne answered it, but maybe I'll ask a, kind of just a corollary question. So my question was, since they're 2D FITS files, presumably there's full FITS header information about the, so you have metadata, so you get information like, like the plate scale of the image as well. So if you're want to do things like template subtraction kind of work, you'd know what the plate scale is, right?
Yes.
Okay. All right. Thank you.
Yep. Yes. So that is one phase of it. And then, of course, even before that is the planning, which I think you guys actually do a lot more than we do, because sometimes we form a committee for outreach or anniversary products where we get to sort of come together and select an object that's not only like scientifically compelling and aesthetically compelling, but also is available to see. So it has to be the right time of year. It has to be, a certain amount of orbits that are not too expensive. And of course, the appropriate amount of filters. So there's this discussion of the planning. And I'm curious if anybody knows what this is.
I want to jump in here before you say that. I just wanted to let the group know I have actually gone to the MAST site and downloaded and played with the data. And it's the same type of files we all do play with for our telescopes. And so I'm positive other people in the group have done this. I bet if we did a raise hands, you'd probably find at least like 10-20% of us have. And I could guarantee Arjun has. If he's on here, he might chime in. But all right, thank you. You can go ahead.
Great. Yeah, no, that's great. I'm so glad that people know about MAST, because like some people are like so surprised that it's available to the public. So it's nice that people have already gotten their hands on it. So this is the Carina Nebula, just in case it just looked a little different. I mean, Carina Nebula is very, very large, and this is a very tiny part of it. And actually, it kind of is not quite part of the Carina Nebula. Carina Nebula is like very, very large. But this just goes to show just all the planning work and sort of all the observations that come together to make this fuller mosaic. So this is just one piece highlighted in yellow, which is one pointing, one observation. And one filter for the Carina Nebula, which we'll just go into the pipeline real quick again, just very, very, very briefly. So this is actually the raw data. This is the first stage. Nothing's happened here. We're just collecting the signal. And so you can see there's a lot of artifacts here from the detector. It's like places where it looks like the way that the detector was adhered to sort of its place. And then we have stage one. So that's where we do things that like we flag dead pixels, we flag sort of the saturated areas. This is where we perform our bias and dark subtraction. So again, very similar things you do with ground-based data that you take on your own. But there's a lot more steps that I'm not even aware of in this sort of whole process. And then stage two is our calibrated image, and that's where we apply our flat field. That's when we perform distortion correction based on how the instrument is in the focal plane. And then we apply our world coordinate system. So we apply the coordinates here. And then in stage three, that's where we either combine or stack all of our one exposures together, or we're combining them with a larger mosaic at the same time. So this is our final products. This is the best science image product that you will get.
Alyssa.
Yes.
Yeah, this is Joseph Novatka. I'm looking at your image and I see that your stars have little holes in them.
Yes.
And I was wondering, is that an artifact of the secondary, or what is that?
That is actually created from the pipeline itself. So when we're flagging the saturated regions, that's actually the maximum, like the value was already, it maxed out right there. So the pipeline, it replaces it with a null value because it's telling the scientist that they can perform any data analysis on it. So it's like a warning to the scientists, not very helpful to the image processors because we have to fill that back in. But I will get into how we fill it back in. But yeah, that's just introduced by the pipeline itself, unfortunately. You can see
that data is then lost.
Yes, exactly. This is our first frame here, and the first frame, it was already bright white. So that gets filled with black.
Right. Okay.
In other words, it's oversaturated.
Yeah, the data's not lost because the data's not any good because it's saturated already.
Right. Okay, so we've already seen it stretch though, so we're actually moving a little bit forward. So I'm going to go back to how we would see it on our screens, and you guys who do any sort of deep space imaging, probably this is how you would see it on your screens as well. So we have to do something first called stretching, and there's a lot of programs that we use that you'll find that you guys use too. It's just whatever works. And it depends on the object. It's not always a one size fits all. So the first thing is, of course, image stretching to be able to see the data that is there. These telescopes are so much more sensitive to light than our eyes. So we have to perform a transformation in order to just show it on our screens. And so, but you can see it is there. On the left is our histogram, but it's all those pixel values or brightness values are sort of pushed up against the left end. But this is a filter. This is one image through the 2.7 micron filter in the Webb deep field, SMAC 1702, I think. And again, it looks black, but again, we have a ton of information that we just need to pull out using specific transformation. And this is like a quick little look at, or a simplified look at stretching. So we have this 2-bit value of a parrot. So 4 values. We have bright white, we have light gray, dark gray, and then black. And then, so on the far left, we haven't done anything, just linear 1-to-1. And then in the middle, we have a linear transformation. As you can see, doesn't really help us because it might bring up some of the, the light or the dark gray, but now we've completely lost the contrast between the brightest point and our dark point. So what we want to do is the nonlinear transformation in order to bring up those bright or dark values, but then not clip our white values. So we want to maintain that. So this is just another look at using the linear stretch on the Webb deep field here. And you can see we've lost all that information. So even though we stretched out this histogram to see all those details in the background, we've lost information in the brightest regions. So we don't want to do that. So that's why we do our nonlinear stretch. It can be a couple of things depending on the data set. But as you see, beautiful histogram, but we haven't lost any of our darkest points or our brightest points. And so
Alyssa?
Yes.
What is this just photo? What software are you using?
So this is actually just DS9, which is not something we actually export from. It's just sort of a visualization software, very quick to see what's going on. But the one that we tend to use, or there's a lot of different ones that we tend to use, but one of them is Fitz Liberator, and it's the one that I tend to talk about just because it's free, and I think most people like free things. So, and you can find it at NORLab at the link below and download it. We have Fitz Liberator 4, which is so great because this is actually kind of new. I think it's been out for like a year or two, but before that it was, I think it was 32-bit limited, so like it didn't work with Catalina and stuff. But anyways, free, and it works very great. You're just usually we apply the arcsine hyperbolic function here. It tends to work the best, especially with sort of these galaxy fields and galaxies in general, and nebula even too. But I find that for like planetary objects, that's where linear is fine, just because they're so bright. But it really depends on the object. You can play around with these different scaling functions and just find it's a nice range where you're stretching out the histogram, but of course you're capturing all the information in there. And then of course there's PixInsight and other programs that we use too, just again, depending on the object. So it really really kind of depends what you want to do. And I'm sure some of you are familiar with PixInsight. It does cost money, but I feel like it's totally worth it because it's not a subscription, which is nice. It's just like a one lump sum. And then
We have another question. Joe, do you want to go ahead?
Yeah, can you hear me?
yes.
So yeah, my other question has to do with the files that you use. Are they all FITS files, or are any of them TIFFs or any other type of file?
They all start FITS files, and then they only become TIFFs after we export them from whatever program we liberate the FITS from. So yeah, they are all FITS files.
But do you get them from the observatory in a FITS file format?
Yes.
Okay, so it's not a direct image.
Right.
All right, thank you.
Yep.
The let me speak up. The downlinked image is not FITS. It's just a stream of bits. But when it gets
Exactly.
onto the ground, it gets converted into a FITS file before anybody sees it.
Right.
Right.
Well, that's what I thought.
Right.
I mean, I worked on the sensors and I worked on the CCDs and things and the imaging sensors. And the thing is that, you know, everything is A to D converted on board, and it should be coming down that way. But I didn't know if the main processors are converting it over on flight.
Mm, I
No,
got
no, the FITS processing is done on the ground.
Yep.
Okay, thank you.
All right. So back to stretching, just real quick. This is an example with the Carina Nebula. So there's 6 different filters. And of course, this is how it kind of appears when we bring it into our photo editing software or FITS Liberator. And we need to bring out those details because, of course, the whole point of making this image is to see the different structures that you're seeing in these different filters that are capturing different molecules, different physical or astronomical phenomenon and things like that. So again, this is our last step to relatively stretch them all the same according to each other. And then once we do that, that's when we assign a color. And we do this in what we call chromatic ordering. So this is something that you guys are familiar with, but some people have this misconception that these images are created in color automatically, but that's actually not how most things work, because even our smartphones have 3 different color channels that combine together to make our color image. And these telescopes work the same way, but a lot more complicated, a lot more filters to work with here. So we have a filter wheel that's capturing specific infrared wavelengths, and then we assign them appropriately depending on what their wavelength is. So that seems a little bit weird and hard, and there is a level of translation and representation here because we cannot see in infrared, but this is how we sort of map color. We map color to the visible based off of how we see visible light. So the lower wavelengths are the bluer colors, and then the longer wavelengths are the redder colors. So we're just shifting that into the infrared, or we're taking the infrared wavelengths and keeping their scale the same and then shifting them down. And so that's how
we have a question from here in the audience.
Yeah.
Hey, so it's Anthony. So it sounds like what you just said is pretty much the optical equivalent for like mixing down in frequency, like for radio frequency systems. And for years I've been questioning that, and nobody could really answer it. But I'm really glad to hear that that's what's happening, because that's an amazing thing, and I was always wondering if that was possible. So it sounds like that's what the Webb does, then, huh?
Yep.
That is wonderful.
Yep.
Okay.
Yep. Yep. And we take these different wavelengths and prescribe the color accordingly to their wavelength. And so when we combine it together, that's how we get our full color image. And so again, we're keeping to the chromatic ordering so that the shortest wavelength, in this case is the 0.9 microns, is the bluest. And then we work our way up to the 4.4, which is red. Now you do see an outlier here, 4.7, which is yellow, which is not an accident for a couple of reasons. This is not really breaking any rules. Well, for one, 4.7 actually is within the 4.4 micron filter, which is a very, very wide filter. And secondly, we also capture this hydrogen feature, which in the 2.2 12 micron filter. And so, but the main reason, of course, is it's not breaking any science, but the main reason is that we do not want to prescribe it red because it's a very important feature. It's very hot hydrogen gas. It's actually showing where these very young hot stars are that you can't see, but you can see the jets from this yellow. If we prescribed it red or orange, it would just get lost in this sea of information. And we really want to be able to see those different structures because we want to understand what's actually happening. And then before I combine all those images together additively to get the color image, we do have to do a little bit of correction because even though it's gone down through the pipeline, there's still some artifacts that remain that we have to fix. There's this banding error that does get a little bit corrected in calibration. It's called 1/f noise, and it's worse for the shorter wavelength channels. And we have different ways of handling that. So we have to apply sort of that adjustment to all of them. Of course, we've been talking about those star cores that shouldn't be black, but have been made black by the algorithm or the calibration pipeline that we have to actually fill in appropriately. So we'll get into that a little bit more detail in a bit. But this is the full sort of color image, the initial color image, before we've done sort of any rigorous color balancing. Now, it's a little bit limited for nebula in terms of color balancing because we don't really have that background sky to neutralize, but we can use the cores of the stars in order to get our white balance, essentially. So that's what we usually start with. And then a lot of it does have to be by eye, unfortunately. Now, when you're talking about deep fields and things like that, we do have sky. There is ways to calibrate that image. And then if you have wider field images, you can perform photometric calibration. But these images are so tiny on the sky that there's really no program that can actually do that, at least yet. Okay, so there's not one point where it goes from objective to subjective. We're sort of weighing these ideals and aesthetics while we're thinking about the science and the message that we're trying to communicate. But there are like aesthetic principles that we keep in mind for every image. So we're always considering things like clarity, that's between sort of the different colors and what they represent, as well as sort of the crispness and using color separation in order to tell that story, and also composition, because your composition, your orientation, your cropping, those choices can actually help showcase whatever science you're trying to convey. So a quick little way of showing this is that on the left, you're probably used to seeing the Carina Nebula in this way, in this sort of landscape format where you have this mountain region on the bottom, and then on the top you have like this sort of sky blue region. In fact, though, on the right, that's what the north up, east left convention or the astronomy convention for up in space is. Now, this wouldn't work too well because first of all, we'd have to crop the image. We'd lose some information. Don't want to do that. It's precious data. And then also it just feels a little bit weird. It's weighted strange. And it really helps to have it in this landscape format because it's actually contextual. So what's actually happening in this space image is these hot stars are radiating this dust. It's like eroding this dust, which is the same thing that happens to mountain ranges from weathering. So it's just kind of nice to have this context, this parallel to what we see in our day-to-day lives, so that even though it's magical and spacey, at least we have some sort of, connection to it. And so this is where I sort of shift this color space into a more sort of complementary blue and orange. And so does it need to do this? This is where it becomes a little bit subjective, but this is where it feels like the separation between the dust and the gas is more prominent. And that's what we want to do with these images, is we really want to contrast these two different processes. And then, of course, we're working closely with the scientists and their data at this stage. And so it's an iterative process. So we're sharing it with them, making sure that we are being true to the data, that we are communicating the science that they want to see in this data. So this is where I go a little too far. And this is the artist in you that sometimes just takes over and you got to pull it back. When you're just trying to like bring out these features, it can get oversaturated. It can get what we call overcooked sometimes. And you need to take a step back and let, the image breathe.
Alyssa, so with infrared light, it's easy to get confused with some of the stars that have become visible because you don't know if you're looking through the dust or if it's in the dust. How do you determine that?
I think the best way to do that is actually to compare it to another image. So if you can look at like a Hubble image, that can kind of help, because if a star that wasn't there in the Hubble image is now there in the infrared image. You can assume that it was obscured by the dust. But it's hard. It's something that we kind of deal with all the time. The really bright stars we know are in the foreground, but anything that's sort of pushed back a little bit, it has to be sort of relied to sort of catalog. So we have to find information about that star and be like, how distant is this star? And this is actually a problem we face when we do visualizations, where we're trying to place these things in 3D space.
Right. But I was asking about the stars that are in the dust and behind the dust. I know the ones visibly could be compared with Hubble or whatever, but I'm curious. There's supposed to be a lot of stars in the dust. But there's also stars behind the dust.
Yes.
And how do you know which one is where?
Yes, so it really depends on how dense the dust is, I suppose. So like the ones that seem like right in front of the red, I think we're just assuming kind of was partially in the dust, but maybe not too far into the dust. But this is probably a better question for a science expert. I don't want to give you any wrong answers. But yeah, I think it depends on that, and a lot of photometry if we have that. So that would be like more of the data analysis stuff. But
do you ever go ahead?
The audience, we got a question here in the audience.
So it's Anthony again. So just related to my question earlier, just curious, when you map the infrared to the visible spectrum, is that hardware related or is that completely programmatic?
That is programmatic in the sense that we won't always get the same filters we need to make a color image. So one wavelength can't always be one color. So, but we try to keep the relationship the same. So yeah, unfortunately we can't make it automatic in the sense that then we'd have to get each filter for every single object in order to make sure that it's like 1-to-1, if that makes sense. Yeah.
Yeah, I got you. Thank you.
So Alyssa, what about if you took the different filters, and you know that some of the dust will definitely go through up in the Miri range, or some of the stars will come through in the Miri range, but up in the near red region, it wouldn't necessarily shine through. So you could subtract the filters off.
Hey Joe, I want to say that maybe we could defer this to a conversation at the end. I think you're getting into the weeds.
Yeah, it's interesting to know, though.
Yeah, that's interesting. I would love to talk about it more. I think when we get into Miri.
Yeah, to interesting to some people.
Yeah.
Sorry, David.
But yeah, when we get into the Miri, stars actually tend to disappear, so it gets a little complicated. But it's all cool stuff.
Daniel, go ahead.
So I think I could describe as a filter, Alyssa, something that allows a certain color of light but blocks out other certain colors of light. Is that a filter?
Yep. That's exactly right.
Because with a filter wheel, because that was pretty interesting with the filter wheel, you can use all colors of the light to make a good colorful image.
Yeah, no, it's true. It really depends on like how much filters was requested of the scientist. But it'd be like sometimes we get panchromatic images where we're just literally just meant to have a very colorful, intricate, detailed image in just all of the filters. But yeah, no, that's exactly what they do.
Right, because if you do every color of the light, all the colors of the light, it makes red, blue, purple. You can use all that color light to make that color image of the astro image. Well, that I kind of understand. It kind of makes sense. Thanks, Alyssa.
So that's great to hear.
Understood.
Oh, and this is our last change after we've talked to the scientists. We're having a conversation of how to bring it all together, what they want to see, and the last adjustments are sort of just bringing it all together and bringing out the local color contrast in the mountain region itself, so we can see the structure. So that's what the scientists were sort of interested in. So that's what leads to sort of the changes, and that's sort of the balance of the aesthetic and the science of the whole thing. Oh, and this is the final image. Sorry. So there we go. And then so that was sort of like a broad overview, and I just wanted to get into like a little bit more of the weeds of the little details of how we create the images, like a little bit of the processes that we use.
Hey, Alyssa, real quick, just a quick question. So so many images are coming out from the web all the time. How long does it take to do one? And it seems like there's 1,000 people doing this, and I know it's just a few. So
Yeah. Yeah. So the ones that are going on Webb telescope.org or NASA are being done by Joe or I. So it really does depend on the timeline of when things are going to be done, which sounds silly. I basically say like it will be done when they tell me it needs to be done, because there are times where science is going to come out with or a scientist is going to come out with a paper, and we want to make sure that we get that out to correspond with that paper, or for like the first images that came out, that was like a very compressed schedule because we had like a month to put together like 20 different images for that whole entire package and the different instruments. So I would say like if it was just like kind of like a regular, like no pressure type thing, a mosaic like this, like the pillars of creation, it might take a couple of days depending on how many iterations we make, because we usually don't just have one iteration. We do a couple and work with the scientists from there and figure out what's the best way to translate this information. And then, but if it's like a comet image or like a planetary image, that could take like a day or less, if it's just like one filter or a couple filters. So it really depends on the size of the mosaic and how many filters we have to work with, and also when the deadline is for the paper, essentially.
Thanks.
Yeah, no problem. Okay, so just going a little back to the stretching, and then of course, we just want to bring out the details in all of the different filters. And then we also want to remove any of the artifacts like black cores of stars. And so there is a couple ways to do this. Of course, you can manually go in there, and then that would be a bright white because that's saturated. So there's actually a way in the calibration pipeline to also just reject this, but it complicates things. It's actually not as pretty as the pure black. So it's a little bit complicated to explain. So it's actually better to do it this way to correct it afterwards. And we use an algorithm called Pixel Clip. It's a JavaScript that you can use in PixInsight that we use, and it's very helpful because we can select sort of this darkest point. So that would be off tolerance. And then anything below that will get replaced by either the nearest neighbor or the brightest region. We find the nearest neighbor, it works the best because once we stack all these images together, that's when we get sort of a neutral white color. It's not perfect, but it's the best thing that we have so far. And again, I'm happy to share if anyone's been working with this and have become frustrated with black cores of stars. And then something to note, if you are working with web data and NIRCam specifically, there's a short wavelength channel and there's a long wavelength channel. So anything that's 2 microns and below, that falls into the short wavelength channel. And then everything that's above 2.7 microns is a long wavelength channel. Why does this matter? Because they're actually different sizes. So when you download the data, you're going to have to basically resize them together. Now they should be aligned. So technically you would only have to scale it up by a factor of 2, or you can take it down by a half, and we'll get to that. So on the left is our 4.4 micron filter that falls in the long channel. And then we have our 2 micron filter, and that's the shorter channel. And normally we scale up by a factor of 2 because we like to get the maximum amount of resolution from those short wavelength channels. But you don't have to if you're trying to save sort of RAM space. It doesn't make a huge difference to scale it down. And it is a factor of 2, and it should be aligned if you do it that way. It's not perfect. The calibration pipeline is not perfect. There can be issues with sort of aligning stars. So you can always do it in PixInsight. You can do it that way. You can do it manually. Again, you might have to tweak things a little bit. And then to deal with banding corrections, there's a lot of plugins for this. There's a lot of astronomy tools for this. And one that we use is Astronomy Tools Action Package that you can find at this link below. And it's like $25, but it's just very helpful. There's a lot of actions that I use all the time in conjunction with other ones. And it just helps to kind of stack them in such a way, and you can be creative to get this removed. And a thing to note, part of this package is the banding correction, which is the horizontal and the vertical banding correction actions. And this works in Photoshop. As you must make sure that the banding is parallel to your X and Y axis, or else it's not going to work. So that's how it sort of determines how to get rid of these striations. And then, of course, they tend to not work as well, these algorithms, on really large images. So you might have to find yourself resizing these images down so that you can take a subtraction from the corrected image, and then you can rescale it back up to take a difference image. Or, sorry, I got that backwards. Where you can subtract it after you've taken the difference image. So that way you're not losing any resolution, but you're still correcting for artifacts. Okay, so you have to apply that to all the different filters. Again, this is 6 different filters. They're the same filters as the Carina Nebula. That's why they look so similar in color palette, because they're showing you the same sort of structures here. So here, the thick sort of dense dust is that reddish yellowish region. And then that gassy haze is, that's the hot gas, or I should say the purplish blue haze is the hot gas. And so you can see it's like really flat at first. And so we really have to make sure that we're bringing out, this is where the color contrast comes in. So we can really showcase the difference between those two physical things that are happening here. And then this is like a little peek at a Photoshop file. This is, I use Photoshop. Sometimes I use PixInsight. Again, it really depends on, sometimes I use both and start with PixInsight and end up in Photoshop. It's really what's best for that particular object. And this is just a bunch of curves and levels adjustments, which I'm sure a lot of you have done, just to really, again, the whole point is to showcase those different features. And having more filters is not necessarily better also. You have to make sure that these different filters are sort of overlapping in such a way that they're not canceling each other out, where you can actually make up the different structures. So it's a little bit of a playing around experimentation to get the best image. And so again, I'm pushing it, the contrast, to again separate everything. So we're starting to get that depth again. We're starting to get that structure. And that's exactly what we want. And a tool that I actually find very particularly helpful for Webb imagery, because there's so many stars, it can get a little bit crazy, is Russell Croman tools, and he's fantastic. And one of the tools that I like to use is actually Star Exterminator. So I can actually see what's going on in the background. So I can actually make those sort of minor adjustments without affecting the stars. So I'm not extracting them permanently, I'm putting them back in, but it's just so I can actually separate the two and work on them separately. Because again, they can get kind of overwhelming. And you can also not necessarily see what's happening in the background. And if you want to bring out the structure in the background, but you don't want to change the stars, which are already bright, it's just like a nice, helpful thing to do. But as you can see, when I extract the stars, I can see the seams that remain from the mosaicing. There's like this little stitching that's happening. It's kind of hard to see, I'm sure, here. But it's there, and I want to fix it. And it's so much easier to treat that without the stars getting in the way and accidentally deleting the star or introducing a new star. We don't want to do that. So this little quick change here doesn't look like a huge difference, but that's me correcting that. And then I get to put the stars back in. And then some corrections are easiest after you've made the full color image. So things like cosmic rays. So those high energy particles that are hitting the detector, which are some things that are things that you probably don't deal with unless you have space imagery, because the atmosphere blocks most of the cosmic rays. But what's nice about cosmic rays is that they only hit a part of the detector at one filter at a time. So, if you get a pure color, just one color, like red or green or cyan, that's not a star. That's actually just a high energy particle. So you can remove that by sampling the background and replacing it, or the closest neighbor. And so I'm specifically talking about, these star forming regions, but of course there's so many different images that we work with. And again, it's not a one size fits all. There's different approaches we take depending on the story, depending on the science, and the needs of the object. In one case is the Torrential Nebula, another star forming region, but with a little twist. So it had 6 filters as well, but we actually end up using 4 filters. And there's a specific reason for this. Because again, sometimes more filters is not better. They can cancel the structures out. So you just can get like a white or a neutral gray look, and you don't want that. You want to actually see defining features. So you don't want it to be too chaotic where you can't discern the information. So one thing that we do to actually help amplify specific molecules or atomic transitions or gases is to actually do something called continuum subtraction. And that's basically kind of getting like a narrow band filter by taking a more narrow filter, in this case, the 3.35 microns in the medium band, and subtracting that from a wide band, either directly above or below it. And that helps us actually key on something called PAHs, or polycyclic aromatic hydrocarbons, which are just soot, but it's very important to scientists and sort of, star forming regions and things. So it's really nice to see that signature and really isolate that from sort of the contaminant light from the spectrum. So that's one thing to really bring that feature out. And that's what we do here. And so we have this, we're going to take away that filter just for a little bit, just to see sort of the contrast that it gives you. But we'll start with just the 3-color image. You can see it starts off pretty flat, and hard to kind of discern these different structures, the cluster, the really bright, dust and the gas. And so we're just slowly, it's being color balanced until we finally get to apply. So that was quick, but then we applied that little filter that I talked about that was the continuum subtraction. And that just really makes those structures pop. And you can see if we just added sort of that filter without doing that subtraction, it would kind of overwhelm the image and give it sort of a more muddy sort of red haze. And so that's why we make these decisions. And then you might make a different decision. But this is sort of what the scientist was, interested in. And so I'd be remiss not to mention, Miri, I feel bad. I've been talking about the NIRCam instrument, but the mid-infrared instrument, you can use it the same way. And again, the file sizes are a lot smaller, so it's a lot easier to deal with. So instead, it's like a couple of megabytes versus gigabytes of information. And you can prescribe them as so. They're all wideband, sort of. They say they're all wideband, but some are more narrow than others. Like 1280 is a pretty narrow one. It also captures the pause that I was talking about. So that's why you can see the highlighting of this soot in blue. So it's just cool. It's more colorful because you're seeing sort of the dust emit now. So it tends to be something very alien to us because it's sort of getting into the space that we're not, we cannot see, even though we cannot see in the infrared in general, but it does get more abstract. And then in terms of deep fields, we have a different style of treatment where we want to enhance the color separation as much as possible. So we're stacking sort of the shortest wavelengths together and then stacking the medium 2 together and stacking 2 of the longest together. And that really helps with the color separation. Instead of stacking them all across the spectrum where it can kind of get hazy, this helps really enhance the differences. And why do we care about that? Because deep fields are showing us distances essentially. So we can say when we look at this deep field here, we know that the brightest things or the brightest like blue parts are the closest things to us, like the foreground stars or like that closer cluster in the front. And then the reddish things are either really far away or they're dusty. So that helps us understand what's actually happening in this image. It also looks really nice. So it's twofold. And this is just sort of a deep field, but this is sort of the initial color composite. And you're just seeing how you have to color correct because you have green. And as most astronomers have to deal with green in their images from color casting. So we have to remove that here. And again, enhance those color separation where the red things are really, really far away. And then when we're dealing with planets, that's a whole nother situation. In this particular case, this is actually 3 different stretches combined together. So it's just like a very manual HDR sort of going on here because we want to be able to see the deep field. Well, it's not a deep field. It just happens to be a field full of galaxies, unprecedented because it's Webb. You don't really see planet images with these like galaxies popping up, but we wanted to keep that. So we have that treatment. So it's very faint. So that's a different stretch to bring that out. Then the rings are brighter. So that's a different stretch. But then the disk itself is very, very bright. So you have to definitely have a different stretch for that to composite it all together and see everything all at once. So that's the treatment for this. This is not very different than anything I've described. I just put it on there because this is just a decision between the last 2 filters, the 4.4 micron and the 4.7. And the 4.7 here is an orange because that actually stands out better against the red versus vice versa. So it's just those little decisions to help things be clear. And that's what we want to do. And then this is just one of my favorite images that came out. This is the anniversary image. This is row O. And I just wanted to show you like a quick little process, just like 3-stage process. This is sort of the initial color composite. After I've done some artifact correction and banding correction. It's hard to see, but there's actually a little bit of an area missing here. That's because there was a failure in the guide star. So sometimes you don't get all of your parts and you just got to fill it in with the best you can. And you can do that with a different telescope that sees in infrared like Spitzer. Now, of course, Spitzer is far lower resolution, so you kind of have to do your best. But I did get to fill that in because the colors were the same. So that's what we're doing here. And then just the final image where it's color calibrated and really just having color separation to really differentiate these different areas between the hot hydrogen jets that are coming out. And then we have sort of this like cocoon where the stars are forming and the dense gas, or dense dust, I should say. Okay, and I've talked a lot about outreach images. So these are the images that were planned to be beautiful. Like that was their intention, to be aesthetic. And of course, there's science with them as too. But 99% of the image you're going to see in mass are actually these they're science images. They're scientists put in their proposals to get this data. They're not thinking like, will this make a beautiful image? They're thinking, I want to get these stars. I want to measure this. So they're not thinking about chip gaps. They're not trying to fill those in. They're not thinking about different integration times. So there's areas that are more noisy than others. So as us as image processors, that's where we get to be a little creative. We have to find ways to fill this in, or, you know, make the signal to noise ratio feel more, you know, uniform. So this is the shortest wavelength filter. So that's why there's chip gaps in here. If you don't dither it, you don't fill in those gaps. So you have to move the telescope in order to fill the gaps, which was not done here. But we can take the closest filter to us and fill it in, those gaps. And then we can also do our best to sort of using those banding algorithms that I was talking about to make it more uniform, using sort of noise algorithms to reduce the noise, but maintain the signal. So we get something that's like this. Now, this is a full color composite if I hadn't treated those gaps and those differences in signal. So you can see like, oh, that's not going to work. So we have to treat all those filters in order to get something more like this, where it's definitely more uniform. You can still push it even farther because we do have hydrogen, or we have molecular hydrogen, and we have hydrogen gas. And so the hydrogen gas is like the magenta area, and then the yellowish area is the molecular hydrogen. So we really want to differentiate again those things, tell the story. So that's like a big, just a bunch of, you know, color contrast adjustments, just contrast adjustments in general, just to really bring those structures out in the end. And then lastly, my last slide here is multi-wavelength. So we don't have a lot of time to like really dig into it, but multi-wavelength is something that we care about too. So when I say multi-wavelength, what I mean is taking data from different telescopes and then combine them together. And things like this get very representative because we're kind of getting away from how our eyes would work. So it's more of a representation to understand what's happening and less of sort of a realistic portrayal of what's going on. So there's different standards here, but you have to be very careful when you make these images because you don't want there to be color confusion. So what I mean by that is you don't want something that's red in this image is actually the near infrared. This is the near cam instrument. So you know that's really far away. So again, we're following chromatic ordering still. So we're still making the highest energy wavelengths, the bluer color, and then the longest energy wavelengths, the redder color. So that all stays the same. We're just making sure that, you know, that stays red. And then the Hubble data, which is the shorter wavelengths, the blue and the green, that stays there. We don't want there's sort of overlapping of colors where we make a Hubble image and it has red. And then we make a near cam image and it has red, if that makes sense. So we really want to carefully map things out for clarity and also just aesthetics. But I think that's all I have. So if anyone has any questions for me, I am happy to ask or discuss. I see Hannah first.
Hannah, you raised your hand?
Yep. Hi, Alyssa. Thank you. This was such an incredible presentation. And also congratulations. I just saw you on the Netflix documentary. So that was very cool to see. I live in Baltimore and I was like, that's just down the street from me.
That's cool.
But I was kind of curious. I am very passionate about kind of the intersection of science and art. And I, you know, consider myself a member of the Hubble generation and really grew up on that imagery and saw, you know, just how it transformed the world. So, you know, with that being said, how did you get into, you know, what you do now? Kind of what's your backstory? Because I know there really isn't like a degree like process telescope imagery. If there was, I'm going back to school. But yeah, I'd love to learn kind of a little bit more about your path and like what got you to where you are now.
Of course, yeah. So my path is meandering, but it does end up, I feel like, in the right place. So I actually started off going to Towson University and I got a degree in art and design. So that was my initial thing. And I loved it and it was great, but I kind of felt because it was a liberal arts degree or a liberal arts college, I should say, I really got to like, you know, put my hands in a bunch of things. And I really like science and math too. And I'm like, you know what, I could go for another degree. Didn't really think about the actual end goal, to be honest. I'm just like, I really love astronomy, always loved astronomy, obsessed with documentaries, which is cool to be in this place now because I'm like, oh, I like, you know, documentaries that I used to watch and like now I get to kind of help with the documentaries. But yeah, again, didn't know what I was doing, but I was like, I just did what I was interested in. So I went to University of Maryland, College Park, where I got a degree in astronomy. Wasn't until junior year that it dawned on me that first Space Telescope Science Institute existed because unfortunately a lot of us don't know local in Maryland that it exists, which is a shame. But I learned about it. And also I was taking my observational astronomy course where you actually you go to observatory on campus, take your own data, perform your own data analysis, data reduction, and things like that. And like, that was all great. And I love the data analysis and stuff, but it was like the point where you could make your own image if you wanted to. And I'm like, that was great. Like, that was the best part. And the data reduction I really enjoyed too. Just seeing an image get clean was so nice, removing all the artifacts. So it didn't dawn on me, I think, until that moment that I realized like those Hubble images, they go through a lot of work, like someone's doing that. So I think that was my first realization. And I was like, okay, I want to do that. Like, how do I do that? And then, so basically I just applied to Space Telescope Science Institute, not necessarily with that in mind, thinking that I could do that, but just trying to be involved in their outreach program, or not even their outreach. What's nice about STSCI is actually it's just so wide, so many different talents. There's writers, there's designers, there's animators, there's, IT, there's scientists, of course, there's engineers. There's just like a very vast array of skills. And so it's like, if you love astronomy and you have some other skill, it's like you can come. And so I basically just applied to STSCI for different jobs until this one came. And basically the resume was like art background and science background. And I'm like, wow, like who would have thought like that niche sort of would come together? So I would say I got really lucky. But I think it really comes down to just doing the things that you enjoy, or getting involved in things that you enjoy and making a place for yourself instead of trying to do it the other way around. If that makes sense.
Yeah, that's all. Thank you so much. I'll probably be reaching out to you later to pick your brain a bit more, but I love that so much. And I'm so glad that, you get to do this, and like your talents and skills have really, transformed the way we view science and the way science is expressed to the world. So thank you.
Thank you.
Okay, Daniel, quick one.
Yeah. One James Webb image I thought was interesting was the cosmic question mark. How did that come out?
Yes. So Joe actually worked on that image, and had we known this would be such a big thing, we would have like done a release on it ourselves. But we were both like, he's like, oh, that's cool. Like these interacting galaxies like make this like question mark. So that's basically what it is. It's like an optical illusion of two interacting galaxies from our perspective aligned to look like a question mark, because like one is pulling in. And I wish I had this image to share, because it actually shows like an image, like a nice crisp image of two interacting galaxies kind of looking that way. But it's really cool. Yeah, like you'll just find like a bunch of these like hidden gems in these images, and they're just so huge. And it's so cool to see people scrutinize them in such a way where like just like looking at everything. So yeah.
Is there a gravitational lensing involved to form that cosmic question mark?
So it's just the perspective of two interacting galaxies, the way that they're warping. There's like tidal tails and things like that. So the way that they have just happened to interact. I'm sorry, that was probably the best way. But I would like to, if I could, I would love to share an image of like two interacting galaxies that kind of look like that shape, and what they might look like if you could see them up close. But yeah, it just so happens to be the angle and the way that these two galaxies are very close together. And so they're gravitationally attracted, and they're warping each other into cool things.
But
so
no
gravitational
gravitational lensing involved?
Not that I'm aware of.
Thank you.
We've got another question from right here in the audience.
So I was kind of wondering, you were talking about the telescope dithering. So down here on Earth, we have like telescope mounts that can do that. So with the telescope floating, like what systems do you have to like make it move where you want it to, point at the target and actually dither?
Yeah, no, so this is great. Unfortunately, I'm not very good at engineering, so I don't know the ins and outs of it, but there are gyroscopes on this telescope that help sort of basically like little thrusters and things to put it in the right angle. So again, I'm not in the control of the telescope, but we do have people in our mission office. Actually at Space Telescope Science Institute, we do have the people there that are actually controlling Webb and Hubble, which is very cool. But yeah, they put in the commands, and the gyroscope makes the adjustments to make sure that first it's going to lock on to certain stars. That's usually what happens first, is there's going to be stars that it can solve, so it knows where to stay locked on, and then it will move according to a specific dither pattern that we input, that the scientists will input. So I apologize if that's vague because I am not an expert at this, but that's the general idea.
That's okay.
That's great. I've got a question.
Yes.
So you mentioned how the signal to noise, or on some of the images that are mostly focused on science, not necessarily outreach, you might have a noisier wavelength than the other. So are there instances when like you collect, so presumably some of the different colors are just brighter, so you need more integration time to get a signal on noise. So are there times when they try to collect data on an object with the different wavelengths to bring this, like, more data for the lower ones, just to bring the signal and noise to similar levels for the outreach kind of pictures?
Yeah, for the outreach, a lot goes into trying to understand sort of the intensity or luminosity of these objects. So a lot of like paper research to be like, okay, in this band, how much flux can we expect, or essentially. So yeah, there is work done. Like, so if we're doing something in like UV, we know we have to put a lot more exposure time into the UV just because it's just less sensitive. So yeah, there are those adjustments that are done for the outreach, but yeah, for like the science, they might not care. So it might not be done.
Cool, thank you so much. Any other questions? Maybe we can go through the rest and yeah, thank you so much. What's next?
Yes, you were wonderful. Oh my God, Alyssa.
And Hannah, what's the thing on Netflix? What's the name of the documentary? I want to go look for it now.
I can't think of it off the top of my head, but it literally just came out. Alyssa, you probably know the title.
Yes, it's part of the Unknown series, which I have to say is a really good series in general. It's Cosmic Time Machine, I think.
Awesome.
Yeah.
I'll go look for that.
Not right now.
Everybody
Alyssa,
go watch this.
I'm a graphic designer. And I also love space, and I'm just so jealous of your job.
Oh, I feel you.
So this whole thing has been really exhilarating. I'm on the edge of my seat listening to you stretching levels and curves on images. I know most of the group here is like right over their head and do not get that. I know that's like the focus of your job, more so than the astronomy. But it's beautiful what you do, and I love it and I appreciate it.
Oh, thank you so much. I
Yeah,
appreciate
I'll add to that. Fantastic presentation and great job.
Thank you.
Okay, so yeah, thank you again so much. You're welcome to stay on if you like. Maybe you can see some of our images, and or maybe there'll be more questions. I will say that it's 8:20 and we're in the Robinson Nature Center, and we a lot of times our meetings kind of drift beyond the 2-hour limit, but we have a hard stop at 9 o'clock. We've got to actually, there's people who need to go home. So so hopefully we'll have time to get through this. So let's just, without any further ado, proceed. So yeah, of course I don't know how to use my equipment here. So let's.
Do you have a page up, page down key?
Yeah,
That's what I'm trying to do, but I have this little remote thing.
Oh,
It's not active unless I activate the screen, but it's not letting me. There we go. All right, so what's out, Phil?
Yeah, so for the monthly solar talk here, we put a couple historical things here. One is these images here you can see were captured in, top ones are 1910, and that's in the calcium line. And the one below is in 1915. And I'm certainly not going to take up all the time doing a big presentation on how this was done, but this was done on plates, glass plates. And they had calculated by moving the slits along to capture the right wavelengths in order to do this. And it's just spectacular, especially when you think about this being, 110, 510 years ago. It's just amazing what they were able to figure out and how to do this without the computers and everything else, and to come up with the spectacular information and then also understand what they were looking at. You know, we just don't realize just how, you know, back in the Albert Einstein days and before that, these people were pretty brilliant.
Oh, yeah.
And so this is quite fantastic, and there's quite a stories behind it. I've got a book called The Sun, which is a reprint of a book that was published in 1910. And it's just amazing how accurate most of it was to what we found with all the satellites and everything today. So I just wanted to bring that up, and if somebody's interested in more information on where to find this, I could drop me an email and I'll get this to you.
Sounds like maybe an Astro School topic for the future.
Yeah, that would be amazing. I need somebody else help. So this one, okay, so before you hit play, so this has been in the news all week. So many of you may have seen this. So arguably, the James Webb Space Telescope may have been the greatest engineering and construction feat of mankind for what everything's done. But I got to tell you, you can't take anything away from the solar probe, because this probe here, this Parker Solar Probe, has flown into the sun's corona, and it survived and recorded this gigantic coronal mass ejection and captured this magnificent video, and is still functioning. I mean, it could have been roasted, everything could have happened to it, all the computer stuff, the bits could have flipped out their brains, and this thing is just unbelievable. I don't know why it took a whole year and to come out, you know, because it was recorded. You could see it September 5th of 2022, but it's spectacular. If this is going to work, we'll find out right now. So Victor, try and run this, please.
How can we withstand the magnetic field?
Yeah. Engineering. So obviously the music is not from the sun.
Oh, yeah.
Alyssa put that in there.
Did I just see the Milky Way go by? Oh, look at that.
And if
Absolutely
you look at
fascinating.
asteroid.gov site and go to the Parker Solar Probe mission, you could read a ton about what this is and how it was done and what you're looking at.
Yeah.
So obviously it's looping a little bit.
What are we looking at?
You're looking at the actual solar probe
that the
getting
surface of the sun?
blasted by, you're looking at the coronal mass ejection.
Oh, you're going through the.
Blasted
It's
right
like,
at it.
just like just
Yeah, it went right through that gigantic coronal mass ejection that happened.
plasma, right?
Okay, so the
Yeah,
stuff in the
giant
background is
and
just
everything
background
else.
stars. Right, we're seeing.
Right.
Yeah, these.
The background,
So
it's just driving through a
billions of
flume.
tons of ionized plasma.
Yeah. That's what I'm talking about. Wow.
There you go, and that's my solar presentations for this month.
Thanks.
I like the music though.
Jim, are you on?
I am. So let's talk a little bit about the shallow sky. A couple weeks ago, comet Nishimura was around in the early morning, but unfortunately, after it survived going around the sun, but it's kind of like dive bombing into the south. So you're really not going to be able to observe it, unfortunately. So if you caught it in the morning, great. Otherwise, maybe catch it in 340 some years when it comes back around again. Next, click. Mercury right now is having its best morning elongation. It's not, if the elongations happen a little bit further into fall, they're even better, but this is going to be the best time to get a morning view of Mercury. It's got its best distance from the horizon in this week. Really is probably the best time. If you're a Mercury fan, get out early in the morning in the pre-dawn sky and catch it. Next. Venus has popped up into the pre-dawn sky, and it's at about 30% phase, 36 arc seconds now. Between now and our next meeting, the phase is going to grow into almost a half phase. And of course, as it grows, it shrinks in size, but it's also well placed if you're up in the early morning. Next. Jupiter is now rising around 9 o'clock, so it's becoming a little bit easier and easier for people to catch it before they turn in for the evening. It'll be heading to opposition November the 2nd. This right now, because of the positioning with the Earth, the Sun, and Jupiter, is a good time to take in the Galilean satellites as they kind of cut in front of the planet or behind the planet. And Sky and Telescope has a great resource there online for you to actually pick a date and time, and it'll position and show you where the moons are, plus list any particular events that are coming up for that evening. So that's a great resource. I use that all the time. Next. Saturn is well placed. It's past its opposition, of course. And the shadow on the globe on the rings has kind of returned, as well as that dark line as the rings cut in front of the planet is kind of like the shadow of the crepe ring or ring C. So it gives this wonderful 3D effect to the planet. You know, that's what kind of makes it such a spectacular jaw-dropping thing to look at. So great, easy time to view it, and it's just beautiful. Next. And for those of you that like a challenge, Neptune reached opposition last Tuesday night. It's at about 8th magnitude. For a larger scope, a challenge would be to see if you can catch Triton, which is its 13th magnitude moon. And again, Sky and Telescope has a great resource that will show you where Triton's position is on any night. And, you know, a lot of people are able to do this, but you kind of need a larger scope, and it can kind of be a fun activity when you have a night with reasonable seeing and good clear skies. Next. So as Saturn is beginning to head towards its equinox, what happens is that the rings will begin to tilt further and further until they're going to become edge on. The orbit of the moons is also doing the same sort of thing. And so right now, actually, the moon Tethys is in a position where it is undergoing transits, where it crosses in front of the planet's globe and also behind. Now, seeing it in front of the globe is going to be very challenging. It's a small moon. Visually, it's going to be darn near impossible. Imaging-wise, if you had a scope like James Willingham's size, you might catch it. But you can catch a visual emergence from eclipse. So the animation here is showing you Tethys is in the shadow of the globe, and then it emerges. So if you're observing, you know, crank up the power to get a little separation from the glare of the planet's globe. Start watching, and you should be able to all of a sudden see Tethys appear. And it's not going to be like on the edge of the globe. It'll appear some distance away from the planet. And between now and our next meeting, those are the 4 times where there's going to be a Tethys eclipse. So again, this is not something that you get to see all the time because you have to have the right alignment. So it's kind of a cool thing that you can kind of try to pick up on and observe.
Awesome.
One more click. And of course, October the 14th, we have got an annular solar eclipse. It is in the western part of the country, so unfortunately here in Baltimore, we're not going to see a lot of it, but it's still kind of neat to be able to observe a partial eclipse. Maybe there'll be some cool sunspots. If you're like Phil and you've got some hydrogen alpha or calcium filters, you can even get an even more interesting image by taking it with that filter in place. The particulars starts at 12:01, maximum is at 1:19, and the partial phase ends at 2:38. Final caveat with that is you need to use solar imaging protection or solar viewing protection. You know, definitely go online and make sure that you are using the correct things so that you don't damage your eyes or your instrumentation.
Right.
And that's the shallow sky from now until our next meeting.
Yes, I know. So Jim, thanks. So it's Phil again. Hey, this is October 14th is a Saturday. So I'm going to be sending out an email, but if you have a solar scope, if you have, you know, glasses, solar, you know, protect clip glasses, bring them out. I'm going to bring out the H alpha scope. I'm going to bring out a white light scope
to Alpha
Ridge, and I'll probably bring out a binocular with filters on both lenses. And so we'll have lots of things going on, including imaging this and everything else. So get out early because when it happens, it's gonna happen fast and be gone kind of fast.
And
So-
if you come out to Alpha Ridge, Ken Saul was nice enough to purchase for the club 250 glasses. So there's eclipse safe glasses. We have 250 of them there in the observatory. So if you come out that day, we'll have those for you.
Right, and if you have multiple personalities, you still only need one pair of glasses.
Nice. Thanks, Phil.
Anytime.
Yeah.
Right on, right on.
And that's part of.
Here all week, trying to be.
This is part of how HAL is participating in the STEM Fest for Howard County this year. That event. Okay, Wayne.
Okay, for our update on what's up in space, I'm going to talk to you about something known as the Hubble tension. This is an issue going on in cosmology caused by measuring the Hubble constant. And basically, there's two methods of measuring this constant, which tells us how fast the universe is expanding. The first one is using the cosmic microwave background, and this gives a value of the Hubble constant of 67.4 kilometers per second per megaparsec. So for every megaparsec in away a galaxy is, it will be moving away from us at 67.4 kilometers per second, 67.4. The second way of measuring it is using something known as the cosmic distance ladder, which basically uses, I didn't put it in here, parallax for very close by, Cepheids and supernovae 1A. And if you measure the brightnesses, you know how far away they are. And that gives a value of the Hubble constant of 73.0 plus or minus 1 kilometers per second per megaparsec. You can see these are not the same numbers. In fact, if you're careful and do the calculation, the difference between these two numbers is actually significant to more than what's known as 5 sigma, which is a statistical measurement. And what that basically tells us is that there's less than 1 chance in 3.5 million that the values are actually the same. That means the two different methods that are used to determine the Hubble constant give you different results. And the big question is why? Well, there's at least two possible reasons, but the two I'm going to mention today is that perhaps the observed Cepheid brightnesses are too bright, and that means that the galaxy is not as far away as it looks, and so that we measure a higher Hubble constant for the redshift that we measure for the galaxy. It looks like it's closer, and so the recession velocity with a closer distance would give you a higher velocity. So it's the 73 kilometers per second per megaparsec. The other one is that the cosmic microwave background measurement basically looks at the cosmic microwave background and the little variations in the temperature and this kind of stuff, the features they see in it, and then they use the cosmological model called lambda cold dark matter, and they then tweak that model until it matches what they see in the microwave background, and then they run that model forward in time to get us to the closer point, and that gives us a 67.4 kilometers per second per megaparsec value. So perhaps there's something that's missing from the cosmological model that's causing them to give us a low value. We don't know that. Well, no, not yet. So Nobel laureate Alan Rees, who works at Space Telescope Science Institute and Johns Hopkins University, and his colleagues, of course, they've investigated an aspect of the Cepheid calibration question, and that's what's really the focus of what we're talking about tonight. Next.
Sorry about that, Wayne.
That's all right. So Cepheids are primarily in extragalactic or in distant galaxies or nearby galaxies, but not in the Milky Way. They're identified by the Hubble Space Telescope observations in visible light because the Cepheids variation amplitude is large. Remember, Cepheids are variable stars, and there's a well-known relationship between the period of their variation and how bright the star actually is. So Hubble looks at the galaxies in visible light, and they find the Cepheids, but then they use infrared observations from Hubble to measure the brightness of the Cepheid. And they want to use the infrared because it's less influenced by the dust between us and the Cepheid, mostly in the external galaxy. And so it gives us a better, more reliable measurement of the brightness. And so if you look in the, well, first of all, the Hubble's got a little bit of a problem in the infrared because there's crowding in the field of view for Hubble. And the images to the right, these come from the paper from Adam Rees and his colleagues. The upper left picture is a Hubble image taken in 0.55 microns, right in the middle of the visible. And this red circle shows you the Cepheid variable, and you see it's well isolated, it's bright and everything else. The image on the right, kind of middle, is Hubble, but at 1.6 microns, where they actually do the brightness measurement. You can see the resolution is a lot lower, and there's confusion, and you don't really know what's going on. So they have to make estimates of the contamination in that infrared image based on the stars they see in the visible image and also some other techniques they use. And they apply those estimates of the contamination and they use them to correct the measured brightness of the Cepheid. However, because they're making estimates of the contamination, this leads to additional uncertainty into their brightness measurements. However, JWST has full resolution at that same wavelength in the near infrared, and so corrections are much easier or even absent. And that bottom of the three images is the JWST image at 1.5 microns, essentially the same wavelength as the HST data to the right. And you can see that the stars are much sharper and much clearer, and so it makes it much easier to see the which star is the Cepheid and actually measure its brightness. And just to be completely above board, the reference to the paper is there on the link at the bottom right. Next and last. Oh, before you go, okay, no, never mind. So Adam Rees and his colleagues looked at two galaxies in particular, NGC 5584 and NGC 4258, and they compared JWST's infrared period luminosity relations for Cepheids with previous HST results. And over on the right-hand side, you can see the two period luminosity relations. So on the x-axis of each of these graphs is the period of the variation of the Cepheid variables, and the y-axis is the observed brightness of the Cepheid variable, again in the near infrared. The white gray points are the Hubble data, and the red points are the JWST data. And the net result of this is that JWST's data confirmed the results that had been obtained with HST, but with much smaller uncertainties. Okay, so what this is telling us is it makes it unlikely that the Hubble uncertainties are not causing the Hubble tension. That's the important part of this particular paper. And it suggests possibly that the cosmological models used in the cosmic microwave background determination perhaps need to be looked at to see if they can find the origin of the effect. So that was what I came up with. Again, the reference to the paper is the lower right. At the bottom, there's a link to a YouTube video from Dr. Rebecca Smethurst, where she has talked about this issue. And that was something else I looked at. And something I didn't get to put on the slides because I just found out about it today is Adam Rees has given a talk on September 12th on exactly this topic, and that video is available through, I believe it's the Space Telescope Science Institute, because that's where the talk was given. And I will place in the chat a link to that video. It's about 25 minutes long. It's very well done. I will warn you, though, it was a scientific conference, so it's kind of aimed at professional astronomers, but it's not specifically for cosmologists or that sort of thing. So it's kind of general, but it is a little technical, but it's worth watching if you got about 25 minutes to kill.
Thanks, Wayne. Hey, so are the implications of this, is there any significant, okay, so now it's expanding faster than they had originally thought. Does that change anything about whether you know, the universe is gonna keep expanding, or is whether it's gonna come back, and has that been determined yet?
Remember, Adam Rees won the Nobel Prize for his part of the discovery of the accelerating universe, dark energy. So the rate of expansion is actually increasing at this point. So if the rate of expansion is increasing, there's no reason to believe it's ever going to stop.
Yeah. Okay. Thanks. Okay, well, unless anybody has any other questions for Wayne, okay, we have one more.
Real quick question. So is the difference that acceleration is I'm just curious what the acceleration value is.
I don't know what the acceleration value is, but I will tell you that the acceleration has been included in the cosmological model.
Oh, okay, okay.
And that's,
so yeah,
and that's dark energy, right? I mean, do we?
Yeah, that's dark energy.
And does anybody know what the heck that really is?
No.
No.
That's why it's called dark energy. We don't know what it is.
Okay.
Right.
Okay, and I just posted that link to the Adam Rees's talk.
All right.
Nice.
Okay, well, let's get into some of the images here. We got 15 minutes left. Steve, are you on?
Yes, I am.
You want to talk about these?
Yeah, I went out to the dark sky site at Artemis, Pennsylvania, and was not really prepared to do much except to see the Milky Way for that I haven't seen in a long time. And I did see the Milky Way. I had my cell phone with me, and I just experimented, and lo and behold, by propping it against my binoculars, I was not using the binoculars, but just propping the phone up, I was actually able to take an 8-second exposure and capture the Milky Way.
It's amazing what these cell phones can do.
It is.
And what do you got on the right there?
Yeah, oh, okay. All right, so this is showing Mimas, which tonight at least is actually at the end of its orbit and is the best chance for you to be able to see it. It's out beyond the end of the rings, and about midnight tonight, it will be right at the end of the orbit. Of course, it's probably cloudy. I can't actually see the sky. But the images below there are showing it moving last night when I was out till after midnight, and I show it coming out from behind the ring. And in the final picture, you can see it quite clearly there beside Enceladus, which made it a good point to spot it.
So you actually captured this picture last night.
Yes.
Okay, now I understand why you sent me a picture at the last minute.
Yeah,
that's awesome.
Yeah, that's it. Yeah. My 14-inch is down. The mount is actually on its way back from being repaired at Celestron. So this was done with my 11-inch alt-azimuth that I have to haul out into the driveway, which I don't do very often. The thing weighs 65 pounds, and I'm a little weak to be carrying that around these days.
All right, let's move on. Thanks. That's very interesting stuff. Anything else on that?
But it shows that you can see Mimas if you want to try to get it when it's out at the end of its orbit. And of course, having the rings fairly flat right now makes cuts down the illumination a little bit, but not much.
Okay.
Yeah.
Next, Daniel Lohan, are you on?
I'm here, Malice.
No, there's two Daniels that sent in pictures this month. Daniel Lohan, are you on? I typed in your name, Daniel Login, incorrectly when I first. Whoops.
No, other pen.
How do you turn the lights down?
Go to bottom, up, where it says 10% or whatever.
Anyways.
I'll get that. You can do that.
Here, could you do that? So these are pictures from star parties, from Almost Heaven Star Party on the right. And the picture on the left, I think he told me was from Maine, from Acadia National Park in Maine. You got some nice Milky Way there. Now
Okay.
here's Daniel.
Okay, do you guys see the cursor, my cursor?
Yeah, no, we can't see your cursor.
But I'll tell you, I went to the I went to the star party at the Glen Old Country School at the Gold Observatory, and I used my cell phone to capture this picture of the Big Dipper, and I thought the picture turned out really well. And below the Big Dipper, below the cup, I captured a plane, a high-flying jet plane flying through, right there, right? That's the high-flying jet plane flying through the Big Dipper.
Can you see my mouse, Daniel?
Yes.
Okay, yeah, that's pretty cool. You had a plane in going through the Big Dipper.
Yep,
Awesome.
and I thought, yes, and
All
I
right.
thought the picture turned out good.
Yeah, sure did.
Thanks.
That's nice.
And
Can
speaking
y'all
of,
hear me?
this picture is sublime.
Yeah, so I was at the Cherry Springs State Park for the Black Forest Star Party this past weekend, actually. And I just also sent it this morning because I just finished processing it. But it's 22 hours of data between a one-shot color and a luminance mono camera. It's just a dark nebula that I thought was pretty interesting and very dim, and I've been trying to challenge myself with really dim objects. So yeah, it was a fun thing to chase.
Object. Wow.
Yes.
And you did it with, you have a very fast scope too, right?
Well, yes, I have a RAS. I have an asymmetrical setup. So I have a Roe Ackerman Smith case grain f2, and then I have a f4.5 refractor taking the same and then combining the data. I'm having a lot of fun with that.
Yeah, this is amazing.
Thank you.
Travis, are you on? So Travis sent these in. I think this is the Heart Nebula, and then the center region. These just a zoom in on the right. Very, very beautiful. I don't have any of the capture details. Joe, are you on? Are you still there, Joe?
Yeah, I'm here.
What'd you do
Yeah,
here?
so I captured this in my backyard with my 8-inch Newtonian. It's an f5. So it's fast, but it also has like a 2-inch field of view, or a 2-degree field of view. And the, this picture, I was having trouble using DSS, deep sky stacker. So I tried Sequator, and Sequator generated me this image of 40 different frames. Each were 2 minutes long. And I was really surprised to see that I got this from not having any calibrations. And, there's some noise in it, but I was very pleased with the result.
Where is your, do you live near the city, or where do you live? What kind of skies?
Oh,
do you...
no, I'm in Frederick, on the west end of Frederick. So
Okay.
I'm close to the mountains.
Oh, that's good.
Yeah.
Well, that's very, very pretty.
I'm not in the mountains, but I'm at the base of the mountain. I can't see anything in the west.
All right, nice share.
Thank you.
Jim?
Yeah, so planet time again. The two big ones are back around, and this is just a couple shots that I got last month. Saturn there, you can just barely see the globe casting the shadow on the rings there on the left-hand side a little bit. And actually visually also, you can see that southern hemisphere is just a little bit like grayer colored than the northern hemisphere. As it warms up, it'll probably come so that they begin to look equal. But right now, if you get out there, this was with a 10-inch scope. And of course, Jupiter with the Great Red Spot and a couple of those cyclone storms down at below the Great Red Spot there. There's white areas. Jupiter's always good for some fascinating stuff that storms and rifts and all sorts of neat stuff there. So two of my favorite objects there.
Neat. And Jupiter's just getting higher and higher in the sky right
Just
now.
getting warmed up. Yep.
Mhm. Awesome. Thanks for sharing.
Yeah, how many minutes or seconds did you take of Jupiter in order to get your detail?
That's basically using WinJo posts to derotate 4 1-minute images. So those are each 1-minute video captures distilled down into an image, and then taking those 4 images and kind of like stacking and derotating them.
Oh, that's super. I haven't tried WinJupos yet, but I'm gonna
it's a great
now
tool.
that I see the results you're getting.
Yeah, it's a great tool, really is. So this one was over Perseid meteor weekend. I did a deep sky sojourn out to like a little corner of Southwest Virginia, West Virginia, and beautiful dark skies, probably close to a Bortle too. This I took with just basically my camera, telephoto camera, simple Canon, and I bought a new star tracker, one of those star adventurer guys. So this was my first effort kind of throwing it on. Really nice piece of equipment. I mean, it's very easy to use. It did a great job tracking. So and this, you can't really tell here, but I mean, you can zoom in pretty well on this, and the stars hold nice pinpoint shape. So I was really, really thrilled with the result from the star tracker and just my simple, Canon camera. No telescope required.
Is this the full image, or did you wind up cropping, or you zoomed in a little?
It's cropped a little bit.
Okay, so you have a pretty wide field of view with that 70 millimeter.
Yeah.
Oh, nice. Phil.
Yeah. So this is the one object that light pollution is your friend.
Always spectacular, man.
And I took this on September 9th. Actually, Victor, this is the one I was imaging when you showed up at Company 7 when I was in the parking lot. And so
If
it
I
hasn't,
would've-
what's that?
If I would have known that, I took a picture of you that day. I would have included the picture of you taking this picture.
Yeah, you can do that. Yeah. Oh yeah, so that was it was a perfectly clear day on a weekend, and there's a lot of activity. You can see the prominences in the filaments and all the other features there. The plages, that's what I was searching for. It wasn't the most spectacular view because of all the activity going on, but it was the view of that day. So I did use this, and I took this with a color camera, but I recorded it in monochrome and then added this color later on, because when you're using the monochrome, you get all the bits. And it came out much better. I took several using different types of whether it was color, monochrome, different formats and stuff like that, and just to see what I would do. And it's been a lot of hours, but
Good, it's all with the filter, the telescope.
Yeah, it's with my H alpha. Yeah, it was with my 60 millimeter lens. So that's from the 60 millimeter lens telescope.
Awesome, beautiful.
H alpha.
Hey, Phil.
Yes, sir.
Yeah, can I ask a question on? Have you ever tried using your hydrogen alpha scope on a distant star like Betelgeuse?
So there's not enough light that get in there from that.
Oh, so it'd be totally black?
Yeah, most likely, but I could try it. I have never done that. Now, what Victor and I did do when we were out at Roadkill, Pennsylvania, that is the name of the place. And I have a 0.6 nanometer H alpha filter that we put on my 5-inch refractor with a solar filter in the front, obviously. Right, and so it was a white light, and we were able to pick out prominences with the H alpha filter using the regular white light telescope with that on the back end. But you gotta know what you're doing so you don't screw up and hurt yourself. So that was great.
Are you on, Rob? This picture was submitted through the Discord group. And I unfortunately don't know much about what this is. Is this the trick?
That's cocoon.
It's the cocoon.
Yeah, the cocoon.
Well, I'm gonna move on. Wayne?
Okay, this is the fireworks galaxy on the border between Cygnus and Cephus, I think it is. Maybe it's Draco. Anyway, it's known for having lots of supernovae. It was a nice, pretty picture, so I took it from Alpha Ridge Park. It's 4 hours and 40 minutes of exposure time.
Awesome.
And this is also from Alpha Ridge with the same setup, except this is the Elephant Trunk Nebula in H alpha. And this is 6 hours and 4 minutes of exposure time. Oh, there's also some luminance in here for the stars.
Nice. Is Alyssa still on?
I'm sorry?
We need Alyssa to put some to get this and put some color into it.
No, I'm leaving it like that.
Arjun,
Yeah, so this is my image of the North American.
you might want to speak up a little because the microphone's up here.
So this is my image of the North American Nebula. This was taken at Alpha Ridge around the same time that Dr. Wayne was taking an image of the elephant trunk. I'd like to thank him for introducing me to plate solving, because before I was pointing a random Carly's Cygnus, and now I was pointing to another nebula. So this is just about like 53 to 54 minutes of exposure through a light pollution filter with a planetary camera. And I think it turned out pretty nice.
And what telescope?
Red Cat 51.
Nice, very nice. And Jared is here in the audience.
I know we're short on time. Elephant's trunk in wide field with a 350 millimeter lens and the 2600 color camera with a dual narrowband filter. And my next one.
Absolutely gorgeous.
Wow.
That is absurdly gorgeous.
That was taken with 2600 monochrome camera and 3 filters, the show palette. And that's about 13, 14 hours of data. I can't remember exactly, from Highland, Maryland. So.
Wow. And what scope is this?
That is a 130 millimeter Meade refractor.
So you've cropped quite a bit.
No, actually not. Well, no, I have. You're right. I did crop about half the picture off.
Yeah.
Focus in on
that. That is really amazing.
That's a wow.
Yeah. And that's it. That's all we have for our presentation today. And actually, we're
1 minute to spare.
Yeah, nice finish.
I really appreciate everybody's lot of pictures that we got sent in today, and thank you all for attending. And I think we might have lost Alyssa, but I'm definitely going to thank her very much in email, and we should all go check out that Netflix video too.
Thanks to Victor for bringing us back into the room.
Yeah, and I'm so happy that I thought it was going to be me and Phil.
Love you guys.
Thank you.
We're all
Don't forget
done on
to
the
kill the
hybrid.
recording.
Yeah.
Okay, gotta run. It's good to see you.
You too. Still recording.
Hi, Phil. Phil, can you hear me?
Yeah.
Betsy Singer said hello tonight at
Oh.
Wine Garden.
Where do I do that?
See ya.
See ya.
Bye, everybody.
Bye.